Have you ever looked up at the night sky and wondered how the moon came to be? A question as old as humanity itself. Through the ages, we've been drawn to that glowing orb in the sky, weaving tales and legends to explain its existence. In ancient times, people saw the moon as a deity or a celestial being. The Greeks spun tales of the moon goddess Selene, driving her moon chariot across the night. The Chinese, on the other hand, believed in a great moon rabbit, tirelessly concocting an elixir of life. Some cultures envisioned the moon as a cosmic egg, hatched from the primordial darkness. Others saw it as a chunk of the earth, torn away in some cataclysmic event. So many stories, so many myths, a testament to our enduring fascination with the moon. But what does science say about the birth of our shiny satellite? Let's delve into the theories and uncover the secrets of the moon's birth. First, we turn to the fission theory, the idea that the moon split off from the Earth. Now, isn't that a thought to ponder? But let's not get ahead of ourselves. What exactly is the fission theory? In simple terms, the fission theory proposes that our moon was once a part of Earth. The thought goes like this: billions of years ago, our planet was spinning at an incredibly rapid pace. So rapid, in fact, that a chunk of the Earth, under the influence of centrifugal forces, broke away and hurtled into space. Think of it as spinning a wet tennis ball. As the ball spins, the water is flung outward due to the centrifugal force. If the spinning is fast enough, the water can be thrown off the ball entirely. That's the basic idea behind the fission theory. Now, this isn't just a wild guess. The theory is based on an interesting observation. The moon's composition is surprisingly similar to the Earth's outer layer, suggesting a common origin. But then there's the moon's size. It's unusually much larger than any other moon in comparison to its parent planet in our solar system. One could argue that this would prove that the moon was not once part of the Earth. Fission theory critics claim if the moon did split from the Earth, why is there no giant crater or scar on our planet to show for it? And how did the Earth slow down to its current rotation speed? These questions remain unanswered, casting doubt on the fission theory. So, while the fission theory paints a fascinating picture of our moon's origin, it's not the only possible explanation. It's like a jigsaw puzzle with pieces that almost fit, but not quite. And that's what makes it so intriguing, the quest for the perfect fit. However, this theory has its critics, and there are other theories to consider. So let's keep our minds open as we continue this celestial journey. Enter the capture theory, which suggests the moon was a wandering celestial body that got caught by Earth's gravity. This theory paints a picture of our moon as a vagabond of the cosmos, a celestial drifter that found itself ensnared by the gravitational pull of our planet. The capture theory proposes that our moon wasn't born from the Earth, but rather, it was captured. Imagine a cosmic game of tag, with Earth as the tagger and the moon as the unsuspecting player who got caught. Sounds fascinating, doesn't it? But let's delve deeper. Despite its compelling narrative, the capture theory is not without its flaws. One significant issue lies in the moon's composition. You see, our moon shares a strikingly similar composition to the Earth, especially in its crust. The moon's crust is rich in oxygen, silicon, magnesium, iron, calcium, and aluminum, much like the Earth's. This begs the question, if the moon was a wandering celestial body, shouldn't its composition be different from that of Earth? Shouldn't it bear the mark of its cosmic journey, the telltale signs of its origin from a different part of the universe? The capture theory also struggles to explain the moon's near-circular orbit. In most cases of celestial capture, the captured body follows an elongated or eccentric orbit. But our moon, it orbits Earth in a near-perfect circle. Furthermore, for Earth to have captured the moon, it would have required an exceptionally precise set of circumstances. The moon would have needed to approach Earth at just the right speed and angle, a cosmic coincidence that seems astronomically unlikely. Still, the capture theory doesn't fully satisfy scientists either. So what's next? The condensation theory posits that the moon and Earth formed together from the solar nebula. This theory, like a seasoned detective, traces the birth of the moon back to the same cosmic cradle as our very own planet Earth. Imagine a vast cloud of gas and dust swirling together in the cosmic dance of the early solar system. This is the Solar Nebula, a birthplace of planets, moons, and other celestial bodies. The condensation theory suggests that as this nebula cooled, solid particles began to stick together, forming larger and larger clumps. Eventually, these clumps became massive enough to attract more matter through gravity, leading to the formation of the Moon and Earth. Now you might be thinking, that sounds plausible enough. After all, siblings do share a family resemblance, and indeed, Earth and the Moon do share many similarities. But here's where the plot thickens. The Moon's iron core is significantly smaller than Earth's, a discrepancy that the condensation theory struggles to explain. You see, if the Moon and Earth truly formed side by side from the same material, we would expect their iron cores to be proportionally similar. But they're not. Earth's core is about 1/3 of its total mass, while the Moon's core is only about 2%. It's like comparing a watermelon to a cherry. This glaring inconsistency is a big red flag. It's like finding out that two siblings who were supposed to have grown up together in the same household have drastically different accents. It just doesn't add up. The condensation theory, while elegant in its simplicity, is akin to a puzzle piece that, despite our best efforts, just doesn't quite fit. This isn't to say that the theory is without merit. It has contributed greatly to our understanding of the Moon's origin and has sparked many a lively debate in the scientific community. And yet this theory doesn't fit all the facts. So we turn to the most widely accepted explanation. Finally, we have the giant impact hypothesis, also known as the Theia impact. This theory transports us back in time, about 4.5 billion years ago, to an era brimming with cosmic chaos. Picture our infant Earth, nestled in the solar system, teeming with potential life. Now, imagine a rogue celestial body, roughly the size of Mars, hurtling through the cosmos. This is Theia, the protagonist of our story. The giant impact hypothesis proposes a dramatic encounter between these two celestial bodies. Theia, on its fateful trajectory, collides with Earth in a cataclysmic event. This isn't a glancing blow or a light tap. It's a full-on, high-speed collision, releasing an unimaginable amount of energy, enough to vaporize Theia and part of the Earth's crust. The aftermath of this encounter is equally dramatic. The material from Theia and the Earth's crust, superheated and vaporized, is ejected into orbit around the Earth. Over time, this debris coalesces and forms what we now know as our Moon. It's an astonishing idea, isn't it? Our Moon, that tranquil orb in the night sky, born out of a violent cosmic collision. But what evidence supports this theory? Well, the chemical composition of lunar rocks, brought back by Apollo missions, is remarkably similar to that of Earth's mantle. This suggests a common origin. Additionally, the Moon's size and its peculiar orbit cannot be easily explained by other theories. Yet, despite its appeal, the giant impact hypothesis is not without its challenges. Some key details, like the exact nature of the collision and the precise mechanism of the Moon's formation, still elude us. Computer simulations have yet to provide conclusive answers, leaving room for debate and further research. This is the theory that most scientists support today, but the mystery isn't entirely solved. So, where does this leave us in understanding the Moon's origin? We've ventured through a labyrinth of theories, each offering a unique perspective on the Moon's birth. The fission theory proposed that the Moon was once part of the Earth, torn away by our planet's rapid spin. The capture theory suggested a cosmic game of tag, where Earth snagged the Moon from its solitary journey through space. The condensation theory painted a picture of the Earth and Moon forming side by side from the same swirling cloud of cosmic dust. And then, there's the giant impact hypothesis, a dramatic tale of celestial collision and rebirth. But even with these theories, the Moon's origin remains a captivating enigma. Each explanation carries its own set of unanswered questions and mysteries. The Moon, our silent companion in the night sky, keeps its secrets well guarded. Which theory do you believe? Did we miss other theories? They can't all be true, right? Leave a comment below. If you made it this far in the video, a very special thanks is in order. If you learned something, like this video, and subscribe to our channel for more.